Okay, the last string I was recording just totally came off the computer, so this will just be a quick explanation of physics beyond the standard model. It's interesting how a person can read different things and understand maybe 3%. The analogy would be reading a novel for a high school novel and being an average high school student and grasping maybe 3% of the meaning of a Nathaniel Hawthorne novel, the Scarlet Letter or something. And reading about things like the Large Hadron Collider, the concepts of matter and antimatter and dark matter and whatever kind of matter, regular matter and dark matter, I guess. It makes one feel like that big sometimes. But also, even though we might feel small by reading it, we also look at the immense, just marvel at the immense genius of it all. Like looking at a great painting or looking at something like Michelangelo, what he did. I'm just reading the words here, just almost spellbinding. Looking at physics beyond the standard model, and people arguing for string theory, or the most interesting thing about the physics beyond the standard model is eventually it's going to be sort of reconciliated with the theory of everything, and that's the theory of everything is a way to bring regular physics into complete compatibility of the standard model of physics with general relativity. The theory of everything. Theoretical physics continues to strive toward a theory of everything, a theory that fully explains and links together all known physical phenomena and predicts the outcome of any experiment that could be carried out in principle. So, in practical terms, the immediate goal in this regard is to develop a theory which would unify the standard model with general relativity and a theory of quantum gravity. Additional features such as overcoming conceptual flaws in either theory or accurate prediction of particle masses would be desired. The challenges in putting together such a theory are not just conceptual, they include the experimental aspects of very high energies needed to probe exotic realms. So, kind of interesting. Extensions, revisions, replacements, and reorganizations of the standard model exist in an attempt to correct these and other issues. String theory is one such reinvention, and many theoretical physicists think that such theories are the next theoretical step toward a theory of everything, the string theory. Theories of quantum gravity, such as loop quantum gravity and others, are thought to be the most promising candidates to the mathematical unification of quantum field theory and general relativity, requiring less drastic changes to existing theories. So there's this mathematical unification that is desired or yearned for among physicists. However, recent work places stringent limits on the effects of quantum gravity on the speed of light and disfavors some current models of quantum gravity. Among the numerous variants of string theory, M theory, whose mathematical existence was first proposed at a string conference in 1995, is believed by many to be a proper candidate, notably by physicists Brian Greene and Stephen Hawking. They both do a lot of writing for the layman too. Though a full mathematical description is not yet known, solutions to the theory exist for specific cases. Recent works have also proposed alternate string theories, some of which lack the harder to test theories of M theory, features of M theory. Also some works by a physicist by the name of Lisa Randall, who has been sort of a trailblazer here with string theory, apparently. So there's the theory of everything. There is something called supersymmetry too. Supersymmetry extends the standard model by adding an additional class of symmetries. These symmetries exchange particles with bosonic particles, such as the symmetry, predicting the existence of supersymmetric particles abbreviated as sparticles. So, which include the squarks and charginos and neutralinos, and it just goes on and on. It's almost as tough as trying to follow all the characters in one of these fantasy books, science fiction fantasy books. It just really gets complicated. Each particle in the Standard Model would have a super partner whose spin differs by 1/2 from the ordinary particle. Due to the breaking of supersymmetry, the sparticles, not particles, but sparticles, are much heavier than their ordinary counterparts, so they are so heavy that existing particle colliders may not be powerful enough to produce them. So, just scraping the surface here in 6 minutes. But I guess my point is that you can read this stuff, and you can actually, the interesting part about it is you can read it, and you can understand it, you can appreciate it at a superficial level, and I'm humble enough to say that I'm appreciating it at a very superficial level. But the fact that I can appreciate it at all is pretty cool. And you know, all these terms, you know, this asymmetry and dark matter and light matter and unification of general relativity versus standard physics. You know, it's amazing stuff. It absolutely is amazing stuff.